again. So this is our third case. My screen is visible. Am I audible?
Yes, sir.
Third case we will consider when input is RAM, right? So let me draw that block diagram again for the system, that is first order system. This is our input RS, this is our output CS, right? And what is CS upon RS? That is 1 upon tau S plus 1. So this we have already seen. Now, in this case, R of S will be equal to 1 upon S square, because input, that is RT, will be equal to T square by 2. This is for RAM. Sorry, RT will be equal to not T square by 2, but RT will be equal to T. Does it not? We have seen this RAM. Yes or no?
Yes, sir.
Okay. So now what we will do is we will substitute the value of R of S. Just see, T of S will be equal to R of S multiplied by 1 upon tau S plus 1. So this will be equal to substituting the value of R of S, that is 1 upon S square, into 1 upon tau S plus 1. Now you have to calculate CT. CT will be equal to Laplace inverse of C of S. That will be equal to Laplace inverse of 1 upon S square tau S plus 1. So now what you have to do, you have to use Laplace, use your partial fraction, and I will leave it up to you to solve this. Will you be able to solve this? Should I directly write the inverse Laplace transform of this function? You just check it, right? If you are not getting, you let me know. But this we have already seen in previous class, so I'm skipping this. So inverse Laplace transform of this function will be t minus tau plus tau e to the power minus t by tau. This is the function that you will get once you will do the inverse Laplace transform. Okay, I've also provided the notes. You can see there, and you can try to solve it. If you are not getting, you can let me know in our next lecture. Then we can solve it. But this is quite easy. By partial fraction, you will be able to do that. So here also, when t is equal to 0, C0 will be equal to how much? Calculate.
Zero.
At t is equal to 0, this will be equal to, just check. So this will be equal to 0 minus tau plus tau e to the power minus 0 upon tau. So this will be equal to 0 tau minus tau plus tau. So this will be equal to 0. And at t is equal to infinite, c infinite will be equal to how much? Infinite minus tau plus tau e to the power minus infinite upon tau. This will be equal to, this term will become 0. So this will be equal to infinite minus tau. So this you can write it as infinite. Is it okay?
Yes, sir.
Okay. So now we will see what is the transient part here. What is the transient part? Can you tell me? This is our transient part. You can see this is our transient part. What is the transient part? That vanishes. At t is equal to 0, you can see this value is equal to 1. At t is equal to infinite, this value becomes how much? This value becomes 0. Okay. This is our transient part. So we can see, right? Transient is equal to y rt t, that will be equal to tau e to the power minus t by tau. This is our transient part. What is our steady state part? By ss t, that will be equal to t minus tau. This is our steady state part. This is our t minus tau. That is, this part is our steady state part, and this part is our transient part. Now, if you want to plot this function, let me just draw. This is our time domain, time axis, and this is our RT, that is input. RT is how much? RT is how much? T, is it not? This is T. Then if you want to draw the response, so its response will be something like this. You can see from here to here, we are having a transient part. You can see here. So this is our transient response, and from this part onwards, steady state response. And we are having a steady state response with an error. This is called as error. Why it is called as error? Because there is some difference between output. This is our output, or we can call it as CT. This is our input, right? There is some error between input and output. And what is the error? You can see here, error is T minus tau, right? So this will give you the pink one is your input, the green one is your output. So this is for ramp function. Now we will see for last function, that is parabola function. Okay. Unit parabola. Here now RT will be equal to T square by 2. Therefore R of S will be equal to 1 upon S cube. Again, CS upon RS will be equal to 1 upon tau S plus 1. This is for first order. So CS will be equal to RS multiplied by 1 upon tau S plus 1. Substitute the value of R of S, that is 1 upon S cube, multiplied by 1 upon tau S plus 1, C of S. Now you want to calculate C of T, that is will be equal to Laplace inverse of C of S. That will be equal to Laplace inverse of 1 upon S cube multiplied by 1 upon tau S plus 1. Now again, I will leave it up to you to calculate the Laplace inverse. I will directly write C of T. So C of T will be equal to T square by 2 minus tau T plus tau square minus tau square to the power minus T by tau. So this will be our CT. Now here again, at C equal to 0, what will be the error? At T is equal to 0, calculate, check it. So this will be equal to 0 minus tau into 0 will be 0, sorry, tau into 2 will be 0, plus tau square minus tau square e to the power minus 0 by tau. So this will be equal to how much? Tau square minus tau square. This will be equal to 0. Are you getting this? At C is equal to 0, at T is equal to 0, the error is, the output is 0. Just check.
Yes, sir.
Okay, I have done nothing but I have put time is equal to 0. So you can see this part will become 0. This part will become 0. This is tau square, and this is e to the power 0. E to the power minus 0 will be, or e to the power 0 is 1. So this will be minus tau square. Tau square will cancel out. So we will get 0. At T is equal to infinite, what will be the output? At T is equal to 0, the output will be infinite. You can see put T is equal to 0, put T is equal to infinite, so our output will be infinite. So here also, if you want to draw, if you want to plot, let me plot. This is time. Let us suppose this is our input function, and our input function is parabola. So it will goes on like this. This is our parabola, that is T square by 2, and output will look like something like this. This is T. This is our CT. This is our C of t. This is also t. You can see here it is also having t square by 2 term, right? So it will also look like something like parabola, but there will be some difference, and it will be error. I have made one mistake at the above figure. Just check. So you can see here at t is equal to 0, our output is 0. At t is equal to infinite, our output is infinite. Or you can also write it as t minus tau. This is our why t minus tau, because you can see here, you can see from here at t is equal to infinite, our let us t minus tau plus tau to the power minus infinite upon tau. So this term will become 0. So our at t is equal to infinite, our output will be t minus tau. You can write it like this, and you can substitute. So this error, this is the error. This is not t minus tau, but the output, the at steady state, the output is t minus tau. And error we will calculate, right? Error we will calculate in next few minutes. Is it okay? The equation of this input is t, and the equation of this output at infinite is t minus tau. Should we move forward?
Yes, sir.
Okay. Now we will calculate errors of all the 4 input that we have seen. Okay, let me draw the diagram. So you can see this is C of S. And what is the gain of feedback? Can anyone tell me again? This is our feedback path. What is the gain of this?
1.
1. So 1 multiplied by what? This is our takeoff point. If CS is flowing in this path, what will be flowing in this path?
CS.
CS, correct? If CS is, because this is our takeoff point, so this 1 into C of S. So that means C of S is flowing here. C of S is flowing here, right? Because 1 is the gain, so 1 into C of S. If anything other it was present, so it will be that quantity into C of S. So this part is called as error, where you compare input and feedback element. So error will be equal to how much? After the summing point, just check. Error will be equal to how much? You have already seen how to solve the summing block, right? What is the error? See the sign of incoming signal. Can't tell me what will be the error. Should this is our summing block? R of S is flowing to positive and C of S is flowing to negative port. So what will be the error? Error is the output, right? What is coming in the input port? Anyone?
Sir, R of S minus C of S.
R of S minus C of S. It is very simple. You can see here R of S is flowing to positive, C of S is flowing to negative. Is it okay? Is it okay to everyone?
Yes.
This is quite simple. You can see C of S is flowing here, so this is our takeoff point. So C of S will be flowing to this part. The gain of feedback is 1, so C of S multiplied by 1 will be C of S. So C of S will be from at this negative point. This is our R of S, which is going to positive. So this is, I'm calling this as error, because when we compare input with the feedback element, that we call it as error. That means, suppose if you are having a car, and if you want that your car should run at 100 kilometer per hour, but right now your car is running at 50 kilometer per hour, so error will be how much? Means how much far it is from the desired result. The car needs to increase its speed from 50 to 100. That means error is 50 kilometer per hour. So you will again press the accelerator, right? So this is the error when you compare input with output. Whatever you want, if your desired response is not according to that, it is called as error. So error will be equal to C of S, R of S minus C of S. You can also write it in time domain by converting, that is ET will be equal to RT minus CT. There is no difference. Now, what is steady state error? Steady state error, we call it as ESS. S stands for steady, S stands for state, and E stands for error. So steady state error, that we can call it as limit t tends to infinite. Why it is tending to infinite? Because it is steady state error. Therefore, we are assuming that, you can see we are having a steady state. Therefore, we are assuming that it is reaching the steady state at infinite time. So, what is the error at steady state? So that is why we are putting limit t tends to infinite et, and et is how much? You can substitute the value, that is limit t tends to infinite rt minus ct. So again, that is steady state error you can calculate by putting limit t tends to infinite rt minus ct, right? This is our steady state error. If you want to calculate what is the steady state error of the system, right? So you can put directly limit t tends to infinite input minus output, right? This is only when valid when your feedback path is, you can see when you are having unity feedback path. What is unity feedback path? Or unity means it is the gain of the feedback path is 1. So then only this formula is valid. Okay, should we move forward?
Yes, sir.
Okay, so this is steady state error. This is how you can calculate in time domain. If you want to calculate in frequency domain, then there is a part that is called as final value theorem. Final value theorem. You can also calculate by final value theorem. Limit t tends to infinite rt minus ct, and when you use for final value theorem, so this will be equal to limit s tends to 0. If t is tending to infinite, s will tends to 0, because this is in frequency domain. So you can see time is inversely proportional to frequency. If time is infinite, frequency will be 0. If frequency is infinite, time will be 0, because time is inversely proportional to frequency. So therefore, s is tending to 0. S term is an extra term. Rest of the things are same. So there is also proof, but proof is not in our course. This is in signals and system. I hope you have already studied. If you have not, then you can look forward. You can study it by your own. So I'm just leaving it up to you. So this is the standard formula for calculating. Have you studied this final value theorem in signals and systems? Initial value theorem and final value theorem, have you studied or not in Laplace? Yes or no?
Yes, sir.
Okay. So again, if you want to calculate steady state error in time domain, so you can calculate in time domain by putting limit t tends to infinite dt will be equal to limit t tends to infinite rt minus ct. If you want to calculate in frequency domain, limit s tends to 0, s e s. This will be equal to limit s tends to 0, s r of s minus c of s. So this is very important. Uh, if you want to calculate the steady state error of any system, then you should have the knowledge about input. You should have the knowledge about output. Again, you should have the knowledge about input and output. Then you can calculate what is the steady state error. Now we will calculate the steady state error of all the input that we have seen for first order system one by one. Right? First case. Again, I will write it down. Ts upon Rs for first order system was 1 upon tau s plus 1, and Ct we have calculated as, let me just check. We calculate Ct. And Ct we have calculated as 1 upon tau e to the power minus t by tau. This is our CT. Now we want to calculate steady state error. So we will calculate it by both ways, and we will check whether both the same are coming same or not by time domain as well as frequency domain. So this will be equal to, first we will calculate by time domain, limit t tends to infinite RT minus CT. Right? If I want to draw, if I want to plot, so this is our RT del t. This is our RT. If I want to plot for CT, this is how our CT will look like. CT. This value is 1 by tau. Is it not? This was our input and this was our output for impulse input. Is it okay? Is it okay?
Yes, sir.
Okay. So now check at t is equal to infinite. What is the value of RT? What is the value of RT at t is equal to infinite? Tell me. When t is equal to infinite, what is the value of RT?
0.
0, correct? Why? Because RT is only present at 0, right? At 0, it is having some finite magnitude. All the other instant, the magnitude is 0. So limit t is equal to infinite, RT is equal to 0 minus CT is equal to how much? This is our transient response, and this is our string. At t is equal to 0, what is the value of CT?
1 by tau.
Why 1 by tau? 1 by tau is only at 0. You can see 1 by tau is the value at where? At 0. What is the value at infinite? I have put question mark also here. You can check.
0.
0. Correct. So you can see 0 minus 0. So PSS will be equal to 0. You can also confirm from here that you can see our input is how much? This is 0. Our output is how much? That is 0. So 0 minus 0 will be 0. So our steady state error is 0. Are you getting my point? Our steady state error is 0. You can compare by input and output, right? Is it okay?
Yes, sir.
Okay. So there is one important point. Any system, just see, is called controlled system. Any system is called as controlled system if output follows input at steady state, or steady state error is as low as possible. Ideally, steady state error should be 0, but it can be present, but it should be very low as possible. So any system is called as controlled system. You can see this control system if output follows the input. You can see output is following. This is our transient state. We do not want to worry about transient state. For calculating error, we only have to worry about steady state. So you can see at steady state, output is following input. Output is how much? 0. Input is how much? 0. So at steady state, output is following the input. So this kind of a system is called as controlled system, right? Or you can also see the error should be as low as possible. Right now, what is the error? Error is 0. Are you getting my point? Should we move forward?
Yes, sir.
Okay. Now we will calculate error by frequency domain. That is final value theorem. Again, limit s tends to 0, s into e of s. That will be equal to limit s tends to 0, s multiplied by r of s minus c of s. What is the Laplace transform of impulse? What is the Laplace transform of impulse? You have seen in
1.
yesterday. 1 minus c of s. C of s is how much? 1 upon tau s plus 1. This was our CS, right? So this will be equal to ESS will be equal to limit s tends to 0 s 1 minus 1 upon tau s plus 1. So this will be equal to how much? So if you put now if you put limit s is equal to 0, then it will be 0 multiplied by 1 minus 1 upon tau into 0 plus 1. So this will be equal to 0 multiplied by 1 minus 1. This will be equal to 0 into 0. So this will be equal to 0. So what is the steady state error coming? What is the steady state error coming?
0.
0. Both from both the way you can see, you can check our steady state error is coming to be 0, right? Which is also true. We have seen in plotted way. So we have also plotted input and we have also plotted output, and we have confirmed that steady state error is coming to be 0. Now we will see for second case. Now RS will be equal to 1 by S. RT will be equal to UT. Our C of S will be equal to how much? 1 upon S multiplied by 1 upon tau S plus 1. This is our C of S. And CT will be equal to, what is the value of CT? 1 minus e to the power minus t by tau. Right. So first we will calculate by time domain. Limit t tends to infinite et. This will be equal to limit t tends to infinite RT minus CT. RT is input, CT is output. If I want to plot, I can plot it also. How RT is, this is our RT, this is 1. This is our RT. And CT is how it is looking. This is again magnitude is 1 and CT is something like this. Is it not? We have seen in yesterday's lecture. So limit t tends to infinite. Now we can directly put the limit. At t is equal to infinite, what is the value of RT?
1.
1 minus at t is equal to infinite, what is the value of CT?
1.
1, correct? That will be equal to 0. So you can see steady state error is 0. You can also verify it from plot, right? You can see at steady state, this is our, suppose this is our transient state and this is our steady state. You can compare input and output. So this is also output is following the input. Whatever our input is, output is following that, right? And steady state error is becoming 0. So you can see that, you can say that this is a control system. You can also calculate from final value theorem, that is limit s tends to 0 s es. That will be equal to limit s tends to 0 s es, that is rs minus cs, that is input minus output. So this will be equal to limit s tends to 0 s into r of s is equal to 1 by s minus 1 upon s multiplied by 1 upon tau s plus 1. So this will be equal to limit take s inside the bracket. So this will be equal to 1 minus 1 upon tau s plus 1. If you put the limit, substitute the limit s is equal to 0. So this will be equal to 1 minus 1 upon tau into 0 plus 1. So this will be equal to 1 minus 1. So this will be equal to 0. Both the ways you can see that we are getting steady state error to be equal to 0. Is it okay?
Yes, sir.
Okay, now we will see for third case. Let me know when it is 8:55, right? Third case. Here R of S is ramp. Ramp is 1 upon s square. RT is equal to T. T of S will be equal to 1 upon s square multiplied by 1 upon tau s plus 1. And CT will be equal to, let me check what is CT. CT is equal to T minus tau plus tau e to the power minus T by tau. This is our CT. If I want to plot it, I can plot it also. Suppose this is our RT, this is T, this is RT, this is T, and if I want to plot CT, let's suppose this is our CT. This is time. If I want to plot in same graph so that it will be more understandable. So let me draw it here also. So this is our CT. Is it okay? Pink line is output, black line is input. Should we move forward?
Yes, sir.
Okay. So now we will calculate error, that is steady state error, limit from time where t tends to infinite, dt. It will be equal to limit t tends to infinite, rt minus ct. This will be equal to limit t tends to infinite, rt is how much? T minus ct is how much? T minus tau plus tau is the power of minus by tau. This is substitute. So this t will cancel out. Limit t tends to infinite, tau minus into minus plus tau minus tau to the power minus t by tau. If you put limit t is equal to infinite, what will be the error? If you put t is equal to infinite, what is tau? Because this term will become 0, error will be equal to tau. So you can see what is the difference between these two is called as error, that is input and output, and error is tau. Here also you can see that our error is not 0 but tau, which is low, which is as low as possible. So this is here also output is following the input. Output is following the input, but there is some small amount of error, that is tau. We can also say that this system is controlled system, right? We can also calculate the error from final value theorem. Let me calculate that also. Limit s tends to 0, s e of s. This will be equal to limit s tends to 0, s e of s, that is rs minus cs. This will be equal to limit s tends to 0, s r of s is 1 by s square minus cs is equal to 1 by s square multiplied by 1 upon tau s plus 1. So this will be equal to limit s tends to 0. Take s inside the bracket, so this will be 1 by s minus 1 upon s into s tau plus 1. Now you can take the LCM, so this will be equal to limit s tends to 0. Take the LCM, s square s tau plus 1. So here you can see s tau plus 1 into s will come minus s will come here. Are you getting this LCM part? I have taken LCM, right? You can take s into s tau plus 1 as LCM also. Is it okay?
Yes, sir.
If you have not understood, let me take LCM again. You can take the LCM in second way, other way also. So limit s tends to 0. If I take LCM, LCM is s tau plus 1. So what will be the factor here? First part, what is not present here? That is s tau plus 1, right? Minus, this is s tau 1 plus 1 is the factor only, so this will be minus 1. Minus 1 plus 1 will cancel out, and s will cancel out. So we will be having limit s tends to 0, tau upon s tau plus 1. If you substitute the limit s is equal to 0, so this will be equal to tau upon 0 into tau plus 1. So this will be equal to tau. Here also error is coming how much? Tau. So from both the ways, error is coming tau. You can see here compared in time domain as well as in frequency domain. Is it okay?
Yes, sir.
Okay.
So it's 856.
Yes. Last case, I'm just writing. You can calculate the error by your own. I'm just writing fourth case. Here, RT is equal to t square by 2. That is, and R of s will be equal to 1 upon s cube. So CS will be equal to how much? 1 upon s cube multiplied by 1 upon tau s plus 1. This is our CS. And CT we have already calculated. I have also provided the notes. You can write down the CT and you can calculate the error in both the ways, right? Can you do it by yourself? Try it. If you are facing any problem, you let me know. Okay. Okay. So in today's class, we have seen how to calculate the error. Error is equal to for time domain, when t is equal to time is equal to infinite, input minus output. This is only valid when we are having unity negative feedback system, right? You can see we are having unity negative feedback, that is feedback path gain is 1. So RT minus CT, that is input minus output. We can also use calculate the steady state error by final value theorem, that is in frequency domain, that is S is equal to S into E of S. So this S into E, S is an extra term multiplied by error. Error is equal to input minus output. So you can see here we have calculated for all the things. That is, first case is impulse, second case is step, and third case is ramp. And I have said that you can calculate it by parabola. Is there any doubt? Okay.